this video, what I'm going to do is I'm going to go through the lighting lab materials and just to show you how we can apply lighting to a model. So you should be familiar with the lab materials, and so all we need to do is download this the project files, which I've already done. And I'm using a Mac, obviously. Should be quite similar if you're using Windows and Visual Studio. So what I'm going to go ahead and do is just run the application. And you can see we're presented with a teapot. This is a standard graphics reference object, and this is a wireframe representation of the teapot, just to show you is actually 3D. So what I'm going to do is turn off the wireframe by just commenting out this GL polygon mode command, and if I run that again, you can see this is the teapot, which is just plain blue, but you can see it kind of without the wireframe we wouldn't know, but this was a 3D object. Okay, so we're going to add lighting to our object, and if I just scroll down on the lab materials, okay, so we're going to add what's called Fong's lighting model, and this is a combination of ambient, diffuse and specular reflection. Okay, I'm not going to talk too much about these in this video. You can go to see these lab notes for more detailed explanation. Okay, to add ambient reflection, okay, this is the ambient reflection equation. So we have Ka, which is a constant, which is just a number, and we have the color of the light, and we have the color of our object. So what I'm going to do first is in the code, okay, so somewhere before the render loop, okay, so here is the render loop, I'm just going to define our object properties. So this is sort of how shiny or how we want our object to be lit. And I'm going to define a float constant, which is our Ka. That's our ambient constant. And I'm also going to define a light color. I'm going to choose a fairly boring one to start with. We're just going to have white. So it's going to be a 3-element vector containing the RGB color values. So for white, we have 111. Okay, and I also need an ambient, the color of the ambient light. So that's light ambient, that's just going to be our Ka, which is our ambient coefficient multiplied by that white color. Okay, so I've defined the color here. I need to send that to the shader. Now we use uniforms to do that. Okay, so I've used uniforms here to send the view and projection matrices to the shader. So I'm going to do something similar. So I'm going to send light source properties to the shader. Okay, so GL uniform it's going to be a vector, so GL uniform 3FV, so it's going to be a 3-element vector. Okay, first I need to get the uniform handle, so get uniform location. Okay, and we're going to use our shader ID, and our name of our uniform is light ambient. Okay, that's the name which I'm going to give it in the shader. I'm sending one vector, and I need a pointer to where that vector is. Okay, just checking that. Yeah. Okay, so that sends it to the shader. Okay, now remember the fragment shader is what is used to give us our colors. So I'm going to go over to my fragment shader. Now at the moment it's fairly simple. Okay, so you can see it's very simple here, and we're going to add. We're going to change this fragment color, but first thing we're going to do is we're going to get the object color. Now this will be from the texture map, so all I'm going to do here is just change from fragment color to object color. So that's from our texture map. Then I'm going to calculate ambient reflection. So this is a 3-element vector. So this is just a color. So ambient is just going to be a color, and that's our light ambient multiplied by our object color. Now at the moment our shader doesn't know what light ambient is because we haven't passed in the uniform, so I'm just going to say uniform is a 3-element vector and it's called light ambient. And our fragment shader, our fragment color is simply at the moment it's just our color of our ambient light. Okay, so let's see if that runs at all. Might have a bug if I've done something wrong. Nope. Okay, so that runs. Oh, that doesn't seem to be working very well. Okay, so I've got a problem here. I'm just going to check. Aha. So you can see this is similar on if you're on Windows, this will be another window, but I'm on Mac, so you can see it says, okay, it doesn't know what object color is. Okay, so what I didn't do here is it didn't define object color to be a 3-element vector. So we'll try doing that again, and I'll run that. There we see. So now you can see we have our teapot, and it looks quite dark. And the reason this looks quite dark is because in our main, when we define the object properties of the ambient constant, that was only 0.2. So if I raise it up to say 0.8 and run it again, okay, it keeps asking for permission. There you can see, so we've got a lighter teapot. So this ambient constant, that controls how bright our teapot looks. Okay, so that's ambient reflection. Now I'm going to go on to look at diffuse reflection. So this is reflection off of dull surfaces. Okay, so I'm bypassing a lot of this. You can read this at your own time. So here we have the diffuse equation. So it's slightly more complicated. So it's some constant kd multiplied by the light color, multiplied by the object color, multiplied by cos theta. And cos theta is the angle between our vector pointing to the light source and our normal vector for the surface. Okay, so what I need to do is back in my main.cpp. So now I need to define kd. I'm going to give it a value of 0.7, and I want to define the diffuse light color. So light diffuse is going to be kd times white. So I'm just assuming that the diffuse is again just kd times white. We also need a position of the light. Okay, with ambient color, it didn't matter where the light was, but now we've got diffuse. We want to know where our position is. Now I'm going to set our light at coordinates 2, 2, 2. Okay, these are just sort of arbitrary chosen. There's no special reason for these. Okay, and we need to send that information to the shaders. Now, the position, this is a world space position. Now, our shaders work in the view space. Well, the fragment shader works in the view space. So what I first need to do is calculate where the view space light position is. Okay, so to do that, I'm going to have a 3-element vector. And this is going to be our view matrix multiplied by a 4-element position vector. So I've got our light position, which is a 3-element one, and I just add or append a 1 to the end of that. So this calculates our light position in the view space. And what I'm going to do is I'm just going to copy and paste that because it's quite similar. Actually, I put this down here. I've actually put it in the wrong place, and I'll copy and paste this code. Okay, so here I've got, instead of light ambient, I'm going to say light position, and that's going to change that to light position as well. And I'm also going to send the diffuse light, so call it light diffuse. Okay, so that will send the light position and light diffuse to the shaders. Now we've got a slight complication here. Now the vertex shader, this calculates the for each fragment, it calculates what the fragment position is. So in our vertex shader, just go down here. At the moment, it's quite simple. So this vertex shader, it outputs. This is the fragment position, and it also outputs our UV coordinates. Now we also need to output the fragment position and the normal for diffuse reflection. So I'm going to add a couple of outputs here. So we're going to output a 3-element vector, which is going to be the position of our fragment. Now that's going to be in the view space. So you might be thinking, hang on, GL position is the position of the fragment. Well, that's in the screen space. Okay, so fragment position, and I'm also going to output our normal vector. So each fragment is going to have its own normal vector. And to do that, so output view space, fragment position, and normal. Okay, so the fragment position in the view space is going to be a 3-element vector. It's going to be view times model. Okay, so here with the fragment position in the screen space, we actually calculated projection times view times model, but we want it in the screen space. So it's just view times model, and that's times a 4-element vector, which is our position of our vertex with a 1 on the end. Okay. For the normal vector, it's slightly more complicated. I'm not going to explain that here. If you want an explanation of why this is so, you can check out the lab materials. It's going to be if I got one less view times model. Oh, inverse view times model, yeah, and that's multiplied by our normal. Okay, so this gives us our view space normal vector. Okay, in the fragment shader, okay, because I'm now outputting 2 more bits of information, fragment position and normal. In the fragment shader, I have to tell it, okay, I've got a fragment position, and I've got a normal. I think that's a uppercase N, isn't it? Yeah. So these have to be exactly the same. So you notice here I've used an uppercase N for normal. It has to be the same as whatever's being outputted from the vertex shader. Okay, now on to our diffuse reflection. I'm going to grab the code from the lab materials rather than typing it out. Okay, that's here. Okay, so I'm going to copy the code for the diffuse reflection. So if we just see what's happening here, we normalize the normal vector, so that makes it gives it a length of 1. Our light vector is the light position minus a fragment position. Calculate cos theta, where we do this using a dot product, and therefore that allows us to calculate the diffuse light. So, and all we do is we add the diffuse color to the ambient color. Now if I run that, hopefully it will run. We've probably got a problem with the shader. If you run it, as I see here, and we're not seeing anything, this normally means we've got a problem with the shader. And again, this window will tell us what the problem is. It doesn't know what light position is. Yes, so I haven't, if we go back to the main.cpp, I sent light position and light diffuse to the shader, but I haven't told it we're going to use it. So all I have to do is then go light position and uniform vec3 light diffuse. Try that again. Hey, there we go. Okay, so this, you can see we've got a much better image of the teapot. The light is somewhere to the right. Okay, if we actually up here somewhere, I'm not plotting it yet, but you can see it's to the right, and we have sort of light and shadow, and we can see the 3D-ness of our teapot. Okay, so the next step is to add specular reflection. Now we've done all the hard work with diffuse reflection, so this is a lot easier. Now specular reflection is reflecting off a shiny object, and most of the reflected light goes towards the reflection vector. And this is how we this is the equation for specular light. Okay, so here we have our Ks, which is just a constant for specular reflection. We also have Ns up here. Now we set these for our object. So let's say we want a shiny object, so we'd have Ks being 1 and Ns say about 20. So back into our code, if I go to main.cpp, so object properties, so I'm going to define 2 floats here. So we got our specular reflection constant, which I'm going to say is 1, and we've also got our specular exponent, which I'm going to give a value of 20. Okay, now all of these properties are set here, and you set these how you want your object to look. So if you want a dull object, you'd set your specular constant to be very low. Okay, now we also got a color for our specular light, so light specular, and that's going to be Ks. Similar to the others, it's going to be Ks times, I'm going to say a white, so our light source is white. And again, got to send those to the shaders, so back into where we sent the others. So I'm just going to do a quick copy and paste for a light diffuse and change that to specular. Okay, and I'm also sending, we also send in the NS. Okay, so it's only a single float, so that's GL uniform 1F. And if I get the shader ID, our uniform is going to be called NS, and the value of that is simply whatever our NS is. Okay, now over to the fragment shader. Now I don't have to mess about with the vertex shader because we've already done that for the diffuse reflection. So first I need to update my uniforms. So this is uniform. It's a 3-element vector. If I can type. So this is light specular. And we've also got a uniform for the NS. My typing's gone right out the window here. And this is a float. And that's just NS. Okay, and again, I'm going to just grab the code from this code here from the lab materials, and this goes into the fragment shader. So you can see what we're doing here. We're calculating our I vector. Now the I vector is the vector from our fragment to the camera. Okay, so that's just whatever negative fragment position is. I calculate the reflection vector. Calculate cosine alpha using the dot product between I and reflection, and then calculate what the specular colour is. Okay, so then all I need to do is add specular to our fragment colour. Let's run that. And you can see what we have here is we have some shiny sort of, in the middle of that teapot, you can see we've got some shiny specular highlights. So that's specular reflection. Just going to check. Where am I going? Oh, yeah. Yep. So you can see here, this is in the main CPP. So we've got the object properties there, and these are light colors and position. And you can see we sent the so after defining them in main CPP, we sent all of the properties to the shader, and then we edited the shader to include the diffuse, specular, and ambient lighting. Okay, well, the next thing we need to do is look at attenuation. Okay, so attenuation, this is the gradual decrease in light over distance, and we can use this equation here to model this. So constant, linear, and quadratic are just numbers between 0 and 1. Okay, so what I'm going to do is in the fragment shader, I'm going to define these here. So if I go float, constant, and we can set these to some values. Now, depending on what these values are, will depend on how quickly the light over distance decreases. So you might want to have a play with these. But I've set these as you can see here. Okay, and I'm going to add attenuation, which I'm going to grab this code here and put it into our code. Okay, we don't need that fragment color anymore. So as you can see here, the distance, this is distance from the fragment to the light position. So light position minus fragment, and calculate the length of that. And then that applies the attenuation equation. So constant plus linear times distance plus quadratic times distance squared. Okay, and if I run that, what will happen? You can see the teapot looks a bit darker than before, but if you really want to see the effect on attenuation, we need some more teapots which are further away than our current teapot. So what I'm going to do now is actually add, instead of drawing one teapot, we're going to be drawing 10 teapots. Okay, so I'm going to grab this code here, and before our render loop, I'm going to paste it in. Now what this code is, it's an array of 10 3-element vectors. Now these give the positions of our teapots, so we're going to draw 10 teapots located at these coordinates. Okay, because we've got multiple objects, instead of just plotting one object, I'm going to plot 10. So this code here, where we calculate the model matrix, send the model matrix to the shader, and then plot draw the teapot, I'm going to replace that with what I just copied. So what this does here, it loops for our 10 objects, calculates a model matrix for each individual objects, and plots it. Okay, in addition to that, I'm going to paste in this code, and this will allow us to draw the light source. Okay, so I'm going to just paste this code straight afterwards. Okay, let's see if that compiles. Yes, it does. And if I run the code, you can see we got multiple teapots. Now if I zoom away, you can see only those teapots which are closest to the light source are being rendered. Now in plotting the light source, that's quite useful, because what I've just noticed is our specular highlights aren't really pointing towards our light source. So I think I might have a bug somewhere. Okay, so let's just have a look through the code. So this is not planned, so I'm just going to have a look through the code to see why have I got that bug. Okay, so something's not quite right. So where we got the view space light position, I'm just going to check all of my code. That's probably from up here. So what I mean is we should have the specular highlights slightly further up the teapot. So I'm just going to double check whether I've got the correct code. I found out where the problem is. Where I sent the light position into the shader, I sent the world space light position, not the view space light position. Okay, so always check your code. You know, if you're getting results which you don't quite expect, just double check. So let's see if that solves our problem. Yeah, there we go. So that's much better. Okay, so if I move the camera further away, I'm not very good at doing this. As you can see, those teapots which are closest to the light source are brighter than the teapots on the left of the screen here, which are further away. So that's the effect of attenuation. And that can be useful if you want, say, like a candle or something in your scene. You don't want the candle illuminating objects really far away. So that's the basic model, Fong's model applied. So that combines ambient, diffuse and specular reflection, and also attenuation. Okay, well that's for a single light source. So what about if we want multiple light sources? Okay, if I'm just scrolling down the lab materials now. Okay, now for multiple light sources, we're going to end up with lots and lots of vectors, lots of constants. So what I'm going to do with multiple light sources is we're going to use a data structure. So I've got a data structure here called light, and within the data structure we've got the position, ambient color, diffuse color, specular color, and also those linear, constant and quadratic attenuation components. Okay, and within the fragment shader what we're going to do is we're going to have an array of these data structures. So for each light we're going to have will be an element of this array lights. Okay, so what I've got here now, this is a actually I just pasted in now. Okay, so what we need to do is I'm just going to copy this and I'm going to create a new shader program, or a new shader fragment shader program. So I'm in Xcode, so I'm just going to add a new file. It's quite similar in Visual Studio. Okay, just for now I'm just going to call it C++. No, I don't want a header file. I'm going to call this multiple lights fragment shader. Okay, and make sure this is an important step here, is make sure it goes in the source folder. Okay, I've already got one in there, but I'll replace it anyway. Okay, what I'm going to do here is another thing I'm going to do is make sure we have the file extension frag. Okay, so this means that what I have here is, I'm going to change this in a minute. Okay, so in my fragment shader I have a frag. Okay, I'm just going to paste in what I've copied from the lab. So if I go through this, so we've got the same inputs as we had before, same outputs. Okay, now I've defined a data structure for my light, and here are my uniforms. So I've got some maximum number of lights, 50. Hopefully we don't need more than that. I've got my texture map. Okay, and one of our uniform is going to be an array of light structures. Num lights is simply how many lights we have, and ns we saw before. Now here, this is our main function in our fragment shader. What I've done is I've written a separate function to calculate what we call a point light. So all of that ambient, diffuse, specular code from before I've put inside a function, just to because in a minute we're going to be adding other types of lights. Okay, and you can see down here. Okay, so For a point light, this calculates the ambient, diffuse and specular reflection exactly the same way as before, and this returns our fragment colour. Okay, so that's our fragment shader done. Okay, we must also have a structure, define a data structure within our CPP code. Okay, so somewhere before where we define our light properties, we need to say, okay, we've got a light struct. Actually, I'm going to put that outside of our main function up here. Okay, so what I'm going to do now is I'm going to get rid of this code here because we don't have a single light. We're now going to have multiple lights. Okay, and oh yeah, so where we compile the shader program, which is further back up, okay, we now got a different shader, so I'm going to just change multiple lights, fragment shader. Okay, and what this code does here, it defines a vector of lights. Okay, and then for each light source we add the position, the ambient, diffuse and specular colours, the attenuation constants, and push back. What that means is it means append this current light onto the end of our light vector. So if I copy and paste that code into our main .cpp, okay, so that means I've now got two lights. One light is at 222 and our second light is at these coordinates. Okay, so this is set back 8 along the z-axis. Oh, looks like I'm missing it. Didn't quite get all of that code. Okay, yes, so I need to send each separate light source to the shader. So for where do I send my light sources? I send them here, so I'm going to replace this code with this. Okay, so what this does is it loops through each of our elements within our lights vector and sends them separately to the fragment shader. Okay, and because we've got multiple light sources, I'm just going to, where we drew the light sources, I'm going to just replace this code with this code. So all this does is loop through each light source and plots it. Okay, let's see if that works. So we build it and let's run it. Okay, so at first glance you think, oh, that hasn't sort of done much, but if I just sort of move the camera around, you can see there's a light source over there, and those teapots on the left, which were further away before, are now lit by the additional light source. So if I just somehow scroll around, you can see, but let's have a look at this teapot straight ahead. Okay, you can see it's got a specular highlights for this light source we can see on screen now. But if I just sort of try and rotate, you can see it's also lit by the light source behind. Okay, so now we've got the ability to add multiple light sources to our scene. Okay. Okay, so that's adding multiple light sources. What we're going to now do is have a look at different types of light source. The first type we're going to look at is a spotlight, and this is essentially a directional light. So, for example, think of a street light that shines straight down. What we're going to do is we're going to restrict the fragments which are illuminated by the light, so that the vector between the light position and the fragment, if the angle that makes between the direction, so this direction vector here, this is the direction but the light is pointing in, and this light vector is the vector from the light to the fragment. If the angle between these theta is less than some angle phi, our fragment's going to be illuminated. But if our fragment, say over here, theta would be greater than phi and it wouldn't be illuminated. Okay, so we're going to add a spotlight to our scene. Okay, so to do so, we need to create a spotlight struct. So where did I create the light struct? So we've got different type of light, so we've got different type of struct. So you can see here it's got much of the same information, but we've also got the direction. So this is going to be a vector, which is the direction of the spotlight, and we've also got cos phi. Now what cos phi is defines how wide our spotlight is going to be. Okay, in our fragment shader, we're going to have to add the uniforms. So if I go to, I'm going to close the fragment shader now, I don't need that anymore. So in our multiple lights fragment shader, okay, so we're going to have a uniform which is going to be some spotlights, and we've got num spotlights, so this is the same, or similar, sorry, to this code here. Okay, now for the point light we used a function, so I'm going to do similar for the spotlight. Okay, so I'm just going to copy. This is called a function prototype. Now what this means is, if I read down the code, for example here, if I go from top to bottom, we've got this calculate point light source. Now if I didn't have this function prototype here, the program wouldn't compile because it wouldn't know what it is, it wouldn't know it's actually a function. So function prototypes are just, we're declaring a function, and down here this is where we actually define our function. Okay, and talking of the function, yeah, I just added that. This is a function for calculating our spotlight, and I'm just going to shove it at the bottom. Okay, so if we have a look at this code, it's quite similar to a point light. Okay, we've got the object color, we've got ambient, diffuse, specular, etc. So all of this code is pretty much identical for the point light. What we have different here is I've calculated the cos theta. So remember, theta is the angle between the light vector and the direction vector. And if cos theta is greater than cos phi, I set a float intensity to 1. And if it isn't, it's just going to remain at 0. So what I then do is I multiply diffuse and specular reflection by my intensity. So this is either going to be 1 or 0 for now. So if our fragment is outside of that spotlight range, we're not going to apply diffuse and specular lighting. Okay, so now we've done with the fragment shader, what we now need to do is actually define a spotlight position. Oh, sorry, I'm not done with the fragment shader yet. We also need to actually call that function. So in our main function within the fragment shader, we're going to loop through the spotlight sources and essentially do very, very similar to what we did with the point light sources. Okay, so now over to our main.cpp. So we've got to define this spotlight struct. Oh, I just realised I might not have done that for the fragment shader. Yes, right. So I think I put it in the wrong place. So in our fragment shader, we've also got to put our spotlight struct, which mean in our main.cpp I've copied over the wrong one. Okay, let's go to our main.cpp. Oh no, copied the right one. Okay, so that's our spotlight struct, and so similar to our point lights, I'm going to down here is define our point light sources. Okay, I'm only going to have one for now, but if we wanted more, we could add them later. And you can see it's much the same way as we've did for the point lights. So here I'm using a direction vector, sorry, of 0, -1, 0. So that's our spotlight's going to point straight down from. It's going to be positioned at 0, 3, 0, and it's going to point straight down. And the angle phi is going to be 45. So notice I've converted it to radians and cosine. Okay, then we've also got to send the spotlights to the shader. So same as what I did for the point light, so nothing's changed here. So after we send the point lights to the shader, I also send the spotlights to the shader. And we've got spotlights now, so let's render them in addition to our point light sources. So that's where we drew the light sources for the point lights. Now I do the same for the spotlights. Okay, let's see if this will run. Oh, I've got a fail build here. Oh yeah, so I did actually put the wrong one in, didn't I? Yeah. So before I put the struct in. So if I just explain what the problem is here, it's C++ doesn't have a vec3 type, not an intrinsic one, so we need to use a GLM type. Okay, so that was the problem there. And you can see it's compiled okay. Okay, let's run that. Right. So, oh, it looks looking a bit bright. So at the moment, if I just zoom back a bit, we've actually got 3 light sources, as you can see here. What I'm going to do is I'm actually going to turn off the spotlights. Sorry, I'm going to turn off the point lights. So all I'm going to do is just comment out where I define the point light sources, and I'll run that again. Just so I just want to show it with only the spotlight. Yeah. So what we've got here, you can see we've got a light source, and it's pointing straight down, and the width of the spotlight is 45 degrees. So you can see only teapots sort of below our spotlight have been illuminated. Now, one thing you may notice here, and I'll just zoom in on it, it's the boundary or the edge between those fragments lit by the point lights, the spotlight, sorry, and those not, is quite sharp. Now, this doesn't really happen in real life. It's kind of, you know, there'll be some sort of fade off there. So we can add that to our shader. Okay, so what I was talking about is this sort of line here. Okay, so let's go back. So, and what we can do is, if this is the intensity, okay, and this is near the edge of our spotlight, so within our spotlight we have intensity 1, outside of our spotlight we have intensity 0, and what we want is a gradual decrease. So we have some small angle delta, and if the angle theta is between phi minus delta and phi, we want it to sort of slowly decrease. And to do that, all we do is we calculate the difference between our angles and divide it by delta. Okay, and this clamp function, what this does is it limits our intensity, so it's within the range 0 to 1. Okay, and here we're using delta of just 2 degrees, so it's quite a small angle. So if we pop over to the fragment shader, I'll go scroll down to where we calculate the intensity. I'm just going to replace those lines of code with this one. Okay, and if we run the code again, right, yeah, so you can see that edge, which I said was quite sharp. Now you can see it kind of slowly sort of fades. Okay, now this is more realistic because in real life you don't tend to have those sudden drop off of light. Okay, so that's a spotlight. Now the final light source or the type of light source we're going to look at is directional light. Now this tends to be from light which is sources far away and also which are quite strong light source. So the classic example is of a sun. Now with directional light sources, each object within our scene will have the same light vector because these light vectors are parallel. Okay, so to add a directional light source, we need to add a struct or a data structure to our fragment shader. Okay, and this is for directional light. And for this, we don't need the attenuation constants because our directional light's not going to decrease in intensity. All we need is a direction vector and our 3 ambient, diffuse and specular colours. Okay, I'm going to pass in a uniform. We're assuming we only have one directional light. You could have more, but I'm going to just assume you've only got one. Okay, so pass in that uniform, and like with the point light and the spotlight, we're going to have a function to calculate that light or the lighting for a directional light, and we're going to just paste in this code at the bottom. So if we have a look at this code, you can see it's similar to the other 2 functions. So we have the object color, ambient, reflection, diffuse and specular. We don't have any attenuation. Okay, so it's actually simpler. The fragment color is just the ambient plus diffuse plus specular. The other slight change is in here. Okay, the direction vector, it doesn't matter where the fragment position is, it's just minus whatever the direction vector is. Okay, so that's the fragment shader done, but we need to define in our main file. Okay, we need to define our directional light. Before I do so, we need a data structure in our C++ file. Okay, so this is pretty much the same as the fragment one, but we needed to use GLM vectors. Okay, and where we define the lighting properties of the others, I'm going to turn on the point light sources on again, just to uncomment that. And we're going to define a directional light, and we're going to define it as a yellow light, just so it's a different color. So I've got a yellow which is red plus green with no blue added. And so you can see direction, so this direction vector is 1, -1, 0, so this is going to come across from the top left as we're looking at it down the z-axis. And you can see we've got the ambient, diffuse and specular. So the last thing we need to do is send that directional light to the shader. Now we've only got one of these for now, so we don't have to use a for loop. Okay, so I'm just going to put that in there, see if it compiles. Okay, it's compiled, and let's run it. Oh, hasn't seemed to work. So at the moment I haven't got any directional light. Okay, so my spotlights and my point light sources are working, but my directional light isn't working. So I'm just going to double check, have I missed something? Oh yes, I know what I've missed. So back into my fragment shader. Okay, so I just missed a scroll back up. Oh, I haven't actually included it on this version. I'll have to edit this. Okay, so you might be wondering why aren't we not seeing a directional light? Well, we have to add the directional light in our fragment shader. Okay, so our fragment color, to that we're going to add the directional light. Okay, so that function there calculated the directional light. So what we got, I got my directional light, my normal vector, and the I vector as well. So okay, let's run this. Oh, so I probably got a problem. So I run that again, you can see we got, oh it's worked that time. I don't know what happened. Okay, so if we have a look at our scene, we've got our 2 point light sources and our spotlight, and we've also got somewhere to the left shining down on our teapots, we've got a yellow light, and you can see that we've given our teapots a bit of a greenish tinge because the light source is yellow and our teapots are all blue. Okay, so I hope that helps a bit. So if you can work through this lab sheet and do this for your own. And then once you've done that, you can then add lighting to your assignment.